So getting into compaction now. Compaction is a densification of soil by removing air voids using mechanical equipment. And so if you look up here, this is kind of what this really means. And so if I have this soil profile right here, this is prior to compaction. However, after I compacted it, if you notice, the volume of air has gone down. And so what we can do with that, by compacting the soil, we can get more material in there. And so basically what we're getting is we're better interlocking characteristics between the soil, and we're also increasing the actual unit weight. So proper compaction provides improved shear strength, improved stability, decreased erosion, permeability, and compressibility. And compaction is typically specified as a percentage of the maximum dry unit weight of either using the Proctor or the modified Proctor test. Some of the factors that affect compaction are compactive effort, soil type and gradation, and moisture content. So with compactive effort, as you'll see on the next slide, compactive effort will actually drive up the maximum dry unit weight. And so all you do is you have a bunch of different curves going up and up and up, as long as they're to the left of the zero air void curve. The zero air void curve actually represents the theoretical limit, i.e. if I took all the air voids out, this is where this would actually coincide with, which typically would be this part over here where the air voids are kind of almost minimal. This would almost rest right on this curve. So the other one is soil type and gradation. It follows that with stronger soils, I will have a higher maximum dry unit weight. So with a stronger soil, we'll plot here, and plot here. And I have a graph on the next few slides that shows this. But then with moisture content, that doesn't affect the maximum dry unit weight. However, it does affect where it plots on there. So with increased moisture content, we'll eventually work our way up to the optimum moisture content, which coincides with the maximum dry unit weight for a given soil. However, once I start adding more moisture, you see the curve start to come down. So with more water, basically it starts almost making the particles float in a way. So you start losing some of that dry unit weight. So one of the things I will point out is when we do compaction, we always specify it as a percentage of maximum dry unit weight. And so whether it's done either using the standard Proctor or the modified Proctor, it's always done as 95% or 98% relative compaction. And so what that really means in essence is 98% line would be here. And so I take the dry unit weight value here and actually multiply it by 0.98, I'll wind up with this value right here, which this kind of corresponds to about 17.8 right now. And so what they can do with that number is use some sort of in-the-field test, whether it be a sand cone test or a nuclear density test, to actually figure out what the density is. So one of the interesting things just to keep in mind is, so if we're going to plot right here, this will correspond with about a 9% moisture content, and this one will correspond with about a 16 moisture content. So if you're in between those values, theoretically you should be here on this curve based on this soil profile as it stands. So there's several methods to actually compact the soil. There's static and impact, vibrating and gyrating, and rolling and kneading. So with vibrating, you tend to have vibrating steel drum rollers, which is done kind of like final rolling, and then you have kneading, you tend to have sheep's foot rolling, which you tend to use on a lot of the clays on the subgrades. So when we start talking about the standard modified Proctor, we talk about compactive force. And so with the modified Proctor, you have a compactive force of over 56,000 pounds, but the compactive force of the standard Proctor is only about 12,500-ish. The difference is when the standard Proctor came about at the turn of the 20th century, they were using compactive equipment that looked like this. And so the compactive force that this early sheep's foot roller could provide was very minimal. And so the standard Proctor worked very well for that. However, as we started getting better and better equipment, the standard Proctor turned out to be inefficient for that, or ineffective for actually specifying compaction, because more and more they would have compaction tests that would come back as 105% or 110%, which doesn't make any sense. So eventually what happened was we started moving to the modified Proctor, which the modified Proctor is now correlated so that the 56,200 foot-pounds corresponds to the newer and heavier equipment that we're using. So basically it's an efficiency thing. So nowadays more times than not, you will always see a modified proctor specified, especially on large-scale projects. And so the big difference is compacted force, and then the other one is there's 5 layers for a modified proctor versus 3 for a standard proctor. And so looking over here at this curve, this is the same soil, just done with different compactive forces. So down here we have a standard proctor test. However, up here we have the modified proctor. So if you can tell, if I was specifying the compaction based on standard proctor, however someone was using an equipment like this, it would plot the soil may plot way up here, and so you'd have a dry unit weight in the field way up here, versus we only specified it at about 109, and so clearly you'd have about 115% relative compaction, versus if I specified it at the modified level at about 119, if I was plotting it right here, I probably wouldn't even be at 95%. So just something to keep in mind. The more compactive force you use, the higher the dry unit weight will actually be in the end. And so as I kind of alluded to earlier, the different types of soils that you're going to use are going to have different dry unit weights as well as different moisture contents. So with the clay, you tend to have a dry unit weight kind of down here. You move up to silt, you're going to be a little bit higher, and then you move up to silty sand, and then eventually you move up to gravels and whatnot, and you'll be having lower water content with high dry unit weights. And so that's kind of the way the soil profile works. And so if there was ever a conceptual question that kind of indicated if the dry unit weight of lean clay was given based on this soil profile and the maximum value was here, if this soil was sandy clay or something like that, where would it plot? And you'd say it's probably higher due to the sand. And so just something to keep in mind. And then obviously the zero air voids line will run right in through here. It's a theoretical limit that chances are we'll never be able to meet, because we'll never be able to get the air voids out of a material. So ways to actually test for field density. We have the sand cone test, the balloon dens, the Shelby tube, and the nuclear gauge test. And so this is kind of a matrix just so you can kind of see the different ways it's done. I'm sure most people who've done an undergraduate CE program have probably dealt with the sand cone test, as this is probably one of the easier ones to do it, in the sense that it's very low cost. However, probably in the field more times than not, you'll see a nuclear density guess, mainly because it's really fast and it's easy to redo once it's calibrated. That's the big caveat with the nuclear gauge, is the nuclear gauge is worthless if it's not calibrated to that local soil, and usually that has to be done in the lab. So, getting into consolidation. So consolidation is actually a lot different than compaction. So with compaction, we're trying to narrow the air voids. However, with consolidation is getting rid of the water. And so what we wind up having is with clay soils take a long time to go from here to here to here, versus a gravel will make that process very quickly. So consolidation is a time-dependent process in certain soils that occurs over time as a result of the pressures from the ground loading pushing the water from the soil layer. Consolidation is a decrease in water voids. Air voids are not affected. And so as I kind of said earlier, compaction is more instantaneous. It decreases the air voids and is applicable to all soils. Whereas consolidation is more time dependent, and it's typically applied to the clay soils that take a long time to actually expel the water out of the layer. And so, as I was saying, consolidation typically affects soil or clay soils due to the low permeability and high plasticity. Other soils typically experience immediate settlement during compaction and loading, so consolidation isn't really a huge issue for them. But with clays, it's a big deal, because in some soils with large amounts of clay with low permeability, it could take over 100 years to achieve complete settlement, especially if it's only one-way drainage versus two-way drainage. And so there's 3 categories of settlement. We have immediate settlement, which happens immediately once the loading is placed on the surface, hence the name immediate. And so we typically look at that as elastic settlement. So then once you get past elastic settlement, we start getting into primary consolidation and then secondary consolidation. And so primary consolidation is the result of volume change because of expulsion of water from the void spaces, whereas secondary consolidation is the plastic settlement of the soil after the primary consolidation is over with. So after the water is pushed out, the plastic settlement occurs where the particles are being realigned to basically compact it even more. And so looking at this next chart, you can kind of see this happening. And so with the initial settlement, you're going to get right into here. You'll see a very slow start, and then all of a sudden it'll pick up. Then when we get into primary consolidation, deformation is going to pick up faster over a shorter amount of time. And then once we get into secondary consolidation, the actual deformation will slow down immensely. And so you'll have a curve that just will continue on and continue on. And so a lot of times with the clay layers, whenever we specify 100% consolidation, typically the answer is the time it would take is unlimited, because we typically just say that it's impossible or we'll never get to that point where 100% consolidation has occurred on a clay layer. However, we could do 95%, 90, 80, or so on and so forth. But stage 1, as I kind of alluded to earlier, is caused by preloading or loading of the actual surface. Stage 2 is the expelling pore water pressure into the layers above and below the clay layer. And then stage 3 is just the plastic readjustment after the expulsion. So stage 3 is also commonly referred to as creep. And so here's kind of what we have here is a typical consolidation curve. So this is actually from a consolidation test on a cohesive soil. So with cohesive soils, you can think clay for this matter. But the consolidation curve follows this black line right here. And so if you notice, we have these two tangents coming off of it. So what these two tangents represent is if I took a linear approximation of this part of the curve and a linear approximation of this curve, I'll wind up at this point right here. And so just for reference, this is called the recompression line, and this is called the virgin compression line. And I'll get into a minute why they're called that. So this at the intersection of these two tangents, I have the pre-consolidation pressure. So there's really no way to actually come up with the exact value of the pre-consolidation pressure, which is why it's typically always approximated or estimated. And one of the most accepted ways is the graphical method, and I will show you that in just a second, how to actually go about doing that. But this pre-consolidation pressure is important, and it's one of the more important things we can pull off a consolidation curve. And the main reason for that is because in this part of the curve, the soil is still considered elastic, i.e., if I loaded the soil up to this pressure but not to the pre-consolidation point and then suddenly unload it, it would come back to this void ratio. However, once I get past the pre-consolidation pressure and say I went to right here and I unloaded it, it'll unload, but it'll unload to a value less than the void ratio. And the reason is because the soil is technically yielded at this point. I've now pushed it beyond the elastic state, and so there's now an over-consolidation that's happened. And so once I've pushed it past that point, I can't go back to the unconsolidated state. So what that kind of alludes to is with this virgin compression line is I can come back to zero stress, however, I'll always have a void ratio or deficiency. But when I reload it, it'll come right back to the point it was on the curve and then start working its way back down. However, when I unload it again, it'll come back at a lower void. And I have another graphical picture to kind of indicate this as well on the coming slides. So say I want to determine the pre-consolidation pressure off this picture right here. So the first thing I'm going to wind up doing is select the minimum point of curvature along the line and along the curve, and I just kind of arbitrarily chose this point. And so what you want to do is draw a horizontal line out from that point straight out along the x-axis. The next thing you're going to want to do is draw a tangential line basically to that point, and so you're going to have these two lines intersecting at your point. Right after that, what you're going to do is take another line and bisect the angle formed by these two. And so I'll have this, and this is roughly approximated. And so then from there, what I'll do is I'll take the remaining part of this curve and draw a tangent up, and that the intersection of the bisecting line and the tangent is our pre-consolidation pressure. So as I alluded to on a few slides ago, after we are going down the consolidation curve and we pass the pre-consolidation pressure, and suddenly we get to point C and we unload at least part of the load, we're eventually going to be moving past it into the unloading curve. And if I unload it to a certain point and leave it there and we get to point D, what we're going to wind up seeing is at a lower pressure, I'm able to maintain a lower void ratio. However, at this pressure on the recompression curve, I would have been at a much higher void ratio. So there's obviously a huge disparity there. And so what we use is the overburden compression ratio to basically tell us at what degree we're over consolidated. And so what we would do is we take the pre-consolidation pressure here and divide it by the pressure here at D, and that'll give us our overburden compression ratio. And so that kind of just allows us to understand the difference between kind of this elastic state and this plastic state down here. And so once again, had I loaded this back and then we went to G and I unloaded it, we'd have a similar curve that you see right here, just a little bit lower down there, but just to kind of help you understand this. And then one more time, just to kind of reiterate this point, with the unload curve, I can unload all the pressure off of it, however I'll never gain back to E. And so getting into consolidation for time, this is probably an ideal question you may see on the exam in regards to consolidation. And basically the question would say something to the effect of calculate the time required for this clay layer to achieve 90% consolidation. Or they may say in X number of days, at what degree of consolidation will this layer achieve? But in any event, you would wind up using this equation right here. And this is equal to, time is equal to the consolidation time factor times the drainage path length squared divided by the coefficient of consolidation. And so the way this is actually going to work is what you do is, say you want to do 90% consolidation, you would come in here to U sub Z, come over to this table and figure out your consolidation time factor is 0.848, plug that in, and then for the drainage path length, you would have to determine whether the soil or the clay layer can drain in one direction or in two directions, i.e. if there's a sand layer above it, then the clay can drain above, and if there's another sand layer below, it can drain below. And so the drainage path length for that situation would be half of the layer thickness. However, if I had the sand layer above a clay layer and then I had an impenetrable or impermeable surface below, then my drainage path length would actually be the layer thickness. And so just something to remember, because HD will either be the layer thickness or will be half the layer thickness, depending on what the actual maximum drainage layer or drainage length is. And then coefficient of consolidation is typically just provided to you in the problem statement. However, if you look in the CU reference manual or the all-in-one handbook, there actually is an equation in there to calculate it. However, you need several more variables to be able to do it.